To demonstrate how to iterate on our private dataset for fire detection model training, we can use the FASTD dataset from the Chinese Academy of Sciences Scientific Data Bank website. This dataset is relatively new and was updated in August 2022. The specific download link is here. Here's an overview of the dataset. FAST contains 101,087 images, including 59,177 positive images, containing 82,666 flame objects, and 57,742 smoke objects, and 41,910 negative images, containing over 60 types of similar but non-fire and non-smoke images. The entire FASTD is composed of two subdatasets, FASTD_CV with 95,314 general computer vision images and FASTD_RS with 5,773 remote sensing images. Fire and smoke objects in FASTD are labeled with the target detection task labels fire and smoke, respectively. FAST provides four types of annotation files. OGC standard format, Pascal VOC format, Microsoft COCO format, YOLO text format. After reviewing the dataset's description, we can confidently conclude that this dataset is suitable for training an initial model. The dataset provides an adequate amount of data, and the label formats meet the requirements. We downloaded the CV version of FASTD_CV, which consists of 12 GB and 95,000 images. After unzipping the files, we found two directories, images containing all the photos and annotations containing four different types of annotations. Upon exploring the VOC directory, we observed that each image has an XML file with the same name, representing the image's annotations. Opening one of these XML files reveals information such as the image name, resolution, and details about the detection boxes for flames and smoke. For instance, there is an indication of a flame detection box with its coordinates and a smoke detection box with its coordinates. The content of the other annotation files is quite similar, with the primary difference being the file format. This diversity in annotation formats allows for compatibility with various popular object detection frameworks, making FASTD a versatile and convenient dataset for fire and smoke detection tasks. Next, we will proceed with creating our dataset. We'll start by creating a test set, which is used to evaluate the model's performance. This is similar to creating a test paper for assessment. The data in the test set cannot overlap with the training data, and the data distribution should be comprehensive. Here, I will create a directory with an arbitrary name, such as eval, and then create two subdirectories inside it, named images and GT. The names are specific and must match to successfully import the data. For the FASTD_CV dataset, the images are divided into four categories: images with both smoke and fire, images with only fire, images with only smoke, and images with neither. I have selected a random sample of images from each category, ranging from 50 to 150 images per category, and placed them in the images directory. The proportion distribution is mainly based on the original data distribution of the images. As I am more concerned about positive samples, I have slightly increased the number of images with both smoke and fire. You can adjust the proportion according to your specific requirements or by annotating actual scene images and adding them to the test set. Finally, I have placed the corresponding XML files, annotations, in the GT directory and compressed this directory into a zip file, following the required format. I have used the same method to create a training set by selecting only 1/12 of the data, which includes over 8,000 images. Although larger datasets generally lead to better model performance, the improvement is not strictly linear with the number of images. Having too many similar images does not effectively improve model performance. However, the computational cost of each iteration is strictly linear with the number of images. If the dataset is too large, the performance may improve by a small margin, but the efficiency of each iteration will decrease. Therefore, it is important to strike a balance when selecting the appropriate dataset size for practical applications. Then we can start training the initial model. After several hours, the initial model will be trained and can be used for demonstration purposes. However, if we want to apply it in real scenarios, we may encounter some issues. If you take a clear look at the images in the FASTD dataset, you will notice that the quality of the negative samples is relatively poor. Specifically, there are not many objects that neither contain smoke nor fire. In fact, there are only 60 types of objects that are very similar to smoke or fire. Therefore, the model's detection performance for real smoke and fire is satisfactory, but for cases that are not smoke or fire, there may be some false positives. We need to add more confusing false positive images to improve the model's performance. To reduce false positives, we need to add high-quality negative samples. In terms of specific operations, we need to leverage our relationship with the client. It would be ideal if we could obtain surveillance videos from the target scene, such as a gas station, or if the client allows us to access the live RTSP stream on site. Offline videos can also be converted into RTSP streams and connected to the edge computing box, where the newly trained flame detection model is deployed. After several hours, all the flame capture results are exported. Since fire incidents in real-life videos are rare events, most of these captures are false positives. We perform manual verification to remove images with actual flames, and what remains are negative samples. This is a negative dataset specific to the target scene. We create a zip package of these filtered negative images, without any annotation data, and import it onto the platform. Then, we switch to the annotation platform and label all of them as negative samples. This operation is quick and does not require much manual effort. We will provide detailed operation manual in the next video of the annotation platform. We continue to iterate on the model in two ways. The first is to start from scratch, adding all the training datasets, including the FASTD dataset and various negative datasets we collected, into the training process. This will take more time, while achieve the best overall performance. The second is to use the previously trained model as the preloaded weights. We select the model and only use the new dataset as the training set, adjusting the number of epochs appropriately. This approach can quickly patch the existing model, ensuring good performance on the new data but potentially affecting the original training results. Therefore, in terms of sample distribution, it is best to match the number of negative images with positive images, keep the ration of positive images to be 0.5 to 0.7. This approach is suitable for rapid iteration processes, such as field collection. In each round, we collect misclassified data, such as dozens to hundreds of negative images, and match them with equal numbers of positive images. It takes only a few tens of minutes to generate a patch model and update it on site. In the second round, we collect new misclassified data, ensuring that we do not receive duplicate misclassifications, saving a lot of time for subsequent manual review and retraining. Finally, when we want to train a model ready for deployment, we can select a larger proportion of the entire FASTD dataset of 95,000 images, along with all the negative datasets, and train from scratch for several tens of hours. The training difficulty will vary depending on the number of deployment scenarios. If we only need to support a few specific locations, then iterating 1 to 2 times on misclassified data can effectively control the false positives. However, if we want to customize support for many locations, we need to collect misclassified data from representative locations and train the model together. This approach will improve the model's generalization and support most locations. For the remaining few locations, we can use the general model as the preloaded weights and add location-specific negative data to quickly train a customized model for that location. Since our edge computing box can update algorithms with one click, it is very convenient to support different algorithms for different locations. As the project progresses, the company will accumulate more and more high-quality data. In the future, we will continue to update the latest and best algorithms, and the company can simply retrain the new algorithms model using these data. This video mainly covers the training with annotated data. In future videos, we will cover the usage of a large amount of unannotated data.